Hello everyone and welcome back to the lecture series of learning theory of automata and formal languages. My name is Binayak Parashar. I am working as an assistant professor in the Department of Computer Science and Engineering at Ajay Kumar Garg Engineering College, Ghaziabad. So, this is a lecture series on theory of automata and formal languages, and we are into unit number 1 and this is lecture number 7. So, basically till now we have tried to come up with a lot of topics regarding the basics related to finite automata. We have discussed the initial part, the languages, then the symbols, then strings, alphabets, okay, and we have tried to got into the formal descriptions of all the automata. We have also discussed the designing process of DFA, we have also discussed the designing process of NFA as well as epsilon NFA and also their equivalence relationships. Okay. So, now in this particular video, let us check it out what is the agenda for this particular video. So, this video we will come across with the finite automata with output, that is nothing but Mealy machine as well as Mealy machine. So, till now we have seen finite automata without output, that is DFA, NFA and epsilon NFA, deterministic finite automata, non-deterministic finite automata and non-deterministic finite automata with epsilon transitions. Now, we will look into a different way of approach, that is finite automata with output. Okay. Here we will not consider any kind of double circular representations which we say as a final accepting state. Okay. Here we will try to look into that how we can count or how we can get the particular string with the help of a particular output alphabet. Okay. So, let us check it out what is there inside this particular lecture. So, first of all, before going into the entire scenario, let us understood the hierarchy in a proper way, which we have already discussed in the first two video lectures. Okay. So, that is finite automata classification. So, finite automata if we talk about, we generally discuss divide this into two approaches, with output and without output. Okay. So, these are the two categories of finite automata, with output, without output. Okay. So, if we talk about with output, this is again segregated into two parts, that is your Mealy machine, okay, and another one is your Mealy machine. Okay. We will try to understand what is the difference between both the machines and which one is like a easy way of approaching. Okay. We will discuss that. We have already discussed the types of finite automata without output, that is deterministic finite automata, in short form we will write as DFA, non-deterministic finite automata which we write in short form as NFA, and the last one is your NFA with epsilon transition. Okay. So, these are the three categories of DFA of finite automata without output. Okay. Now, let us concentrate only on this particular part. Okay. This has already been done. Okay. So, let us check it out in the third slide sorry. We will be discussing about first of all Mealy machine and then we will check our Mealy machine. Okay. So, if we talk about Mealy machine in a short way, I just want to go back and I want to make you remember this thing is that here output is associated with states, okay, and here output is associated with transitions, or we can say output is associated with the inputs. Okay. This is a way of just remembering how like these machines will work in order to understand the difference. So, first of all, if we talk about Mealy machine, the first line says that Mealy machine is a finite state machine where the output is associated with states, So, this is very important point in order to remember Mealy states, Mealy input transitions. Okay. So, with states. So, therefore, if we look into the particular formal description of a Mealy machine, it is divided into not 5 tuples, 6 tuples. Why one extra one? Extra one is for the output transition. Okay. So, let us check it out what are the tuples. First one is your Q, which we already know that finite set of states, sigma, which we already know that the finite set of input alphabets or symbols, then O. Okay. This is a new symbol that you are getting. O is a finite set of symbols called the output alphabet. Okay. This output alphabet will define you whether the string is accepted, whether the count is accepted, okay, how you are counting the particular occurrences. So, everything will be decided by this output alphabet. Sorry. Next comes is your transition function. Okay, delta we already know, this is your input transition function. Here we will not define as a transition function, here we will try to define it as an input transition function, and we will have one more, that is capital letter X, and capital letter X is nothing but the output transition function. Okay. So, some way or the other in our previous that is diagrams, that is finite automata without output, that is DFA and FA, we are having a final state. Here we will not have any final state, rather we will be having a final output, okay, or we say that output alphabet. Okay. Next comes Q naught is the initial state, and then finally we can define this transition function, output transition function, input transition function and output transition function. How? See, here the transition function will represent the same as in the case of DFA. The transition function for Murray machine, input transition function for Murray machine as well as for Mealy machine will be exactly same. Let us go into the second slide and next slide, and I will show it to you. See, transition function, input transition function for both Murray and Mealy, are exactly same. Only the difference will lies where? In the output transition function. So, output transition function, what it says, that in the case of Murray it is associated with states, therefore, output, the number of states are associated with what? Output. Okay. And if you look into this particular Mealy machine, the number of states are associated with the inputs through the transition, correct. This is the output alphabet. Output alphabet will be required in both the cases, for Murray also, for Mealy also, but in Murray this output will be associated with the number of states, and in the case of Mealy this output will be associated with the number of input transitions, correct. So, this is what the small difference between Murray and Mealy. So, I hope the Murray machine formal description is clear to you all. Let us go to the Mealy machine part. So, Mealy machine, again I am trying to depict the entire statement. The Mealy machine is a finite state machine where the output is associated with the present state as well as the present input. See, what is this meaning? I am telling you that Mealy machine, the output is associated with the input transitions. How do you come across with the input transition? Definitely you should start off the present state, and then you will be going with the input transition, right. So, that is why it is said the present state as well as the present input, got it. We will discuss with an example properly, but at first you just try to understand the definition part. Okay. Next comes the formal description. Formal description again comprises of the 6 tuples only, where Q finite state of states, sigma finite set of input alphabets, O finite set of output alphabets, delta input transition function, capital letter X is the output transition function, and Q naught is the initial state. Where I have tried to define you the input transition function for Murray and Mealy are exactly same, only the difference lies in the output transition function. Okay. So, I have told you that in the case of Murray machine, in output transition function, output alphabet is associated with the states, and in the Mealy machine, output is associated with where? Input present state as well as the input transition, okay, or input. Okay. So, this is all about the Mealy machine formal description. Now, let us check it out in the next slide, how to design a Murray machine and how to design a Mealy machine. Later on in the next video lecture, we will look into the equivalence of this Murray and Mealy machine. Okay. Here already I have given you the diagram, but somebody other I will try to let you know that how this process is going on. Okay. So, the question comes here is that construct a Murray machine that prints A, whenever the sequence is 0 1, whenever the sequence is 0 1. So, I can help you out with one more thing is that, okay, whenever the sequence is 0 1, that means input is what? Input is 0 1, then the output should be what? A. This is what exactly it's the meaning of this language. Okay. Construct a Murray machine that prints A. Prints A means will be output will be A whenever the sequence is 0 1, okay, is encountered in any input binary string, and then convert it as. So, conversion process, this particular part I will be not doing in this particular scenario. We will be discussing only the designing part of this Murray machine. Okay. Now, if we look into this particular concept, how to do it. So, I will be discussing this diagram later on. First, let me show it to you what is the easy way of approaching it. Okay. 0 1 is the encountered sequence, right. So, I will be describing like this 0, okay. So, 0 1 I got it. Now, I will be taking this state as suppose A, this state as B, this state as C. So, whenever it says that whenever 0 0 1 is encountered, output should be what? It should print A. So, therefore, and on one more thing, Murray machine, in Murray machine output is associated, output alphabet is associated with states, not the input transition. Therefore, I will write like this A, clear, got it. Now, since we are having two input strings, so I will try to take one more output alphabet as B. You can name anything, it is not mentioned over here, but you can take in your own. That means, whenever B output will be encountered, that is not the string which this language is asking about. Okay. So, therefore, other than this particular state, other outputs will be what? All will be B. I hope this particular concept is clear to everyone. Okay. State I have taken, input transition is what? 0 1, the basic input I am taking 0 1. Okay. Whenever 0 1 sequence comes, then output should print as A, otherwise it should print as what? B. So, otherwise part is not asked in the question, but you should logically think of it, clear. Now, look into the diagram. So, look into the diagram, the same, okay, the same states has been mentioned. So, nothing worries. A, okay, then this part I think it is clear to everyone. Okay. Now, comes to the concept of DFA part. Okay. Now, if you look into the DFA, we have a concept of restriction, that for every input transition there should be exactly one transition going to the next state or to itself, correct. The same concept, same logic will be applied over in Murray and Mealy also. So, that means we cannot have this kind of concept, NFA kind of concept we cannot have it. Okay. We have to do a restriction part, that means from the state A 0 is already been transferred, now I have to look into 1. Now, I have to check that whether I can take a self loop of 1 or not, or I can transfer this 1 to some other position. See, if I transfer this 1 to state A to state B, if I transfer this thing, then this will not be possible, because 1 1 sequence also showing what? Output as A. So, that is not being asked here, 0 1 will show the output as A. So, therefore, this particular line transition we cannot include, clear. So, therefore, finally, I can also do one more thing, that for 1 can I take a self loop. If I take a self loop, it will not at all hamper the sequence. See 1 1 1 1 1 0 1, what is the output it is printing? A only. So, therefore, I can take a self loop. So, this is perfectly done, clear. So, A state is done. Now, I come to B state. In B state, I have already one transition, input transition for 1. Now, let me concentrate on B on 0, correct. So, if I take a 0 transition from here, then definitely 0 0 will give you the output as A, which is possible? No, it is not possible. That means, I cannot take this particular transition. Now, I have to concentrate on the loop part. Can I take a self loop, or can I take a backtrack? I can take a backtrack also, okay. But if I take a backtrack, it will not hamper anything, but let me take a loop. If I take a loop, then 0 in between 0 0 0 0 0 0 1, that means there will be 0 1 together, after that it will print A. So, I can take a loop of 0. So, therefore, state B is also done. Now, come to state C. If we look into state C, in state C there were no transitions coming out for 0 as well as 1. So, what I can do is that for 0 I could have, can I take a self loop over 0? I cannot take. Why? Because it will also produce this kind of sequence. See 0 1 0 1 0 will also produce as A, which is not asking in the language. Therefore, I cannot take a self loop over here. Please, these kind of things you need to practice, otherwise it will always be a little bit of hesitation in designing this kind of machines. Okay. Now, what I can do is that 0 I can take to a dead state, okay, but I will not be using this kind of concept. Why? I can take a backtrack. If I take a backtrack 0 again 1, then definitely 0 1, what is the sequence it is producing? A as the output. So, therefore, it will be a perfect way of representing. So, 0 is done. Can I take 1? 1 I cannot take 1 from this particular state C state to B state. Why? because it will have a sequence 1 1 which is not been asked in the question. So, what I can do, I can take a self loop, I can take a backtrack of 1 back to A. So, it will not at all hamper our diagram. So, this is also done and state C is also done. Now, look into this diagram, this is the perfect Murray machine for this question. Okay. So, this is how you need to construct a Murray machine if a particular question is given to you. You just need to focus that we are not having any such kind of things, final state representation we are not having. We are having a final output alphabet which will define that this is the sequence and this is meeting up with the language. Clear? So, let us go with another question and let me check it out. Okay, fine. Now, I will be looking into, before going into the question, we can understand, we shall get back to you the transition table for the Murray machine. Okay. If you remember, the diagram was like this. Okay. Diagram was like this. A, okay, here we are having B, then B, here we are having B, and then here we are having C, okay, and this one was producing as A. So, whenever the output sequence is 0 1, then it is producing as A, okay, 0 1, okay. Now, can I take a self loop of 1? Yes, I can take it. 0, I can take it. From here it was a 0 and from here it was a 1. So, I think this is the diagram which was been given from the previous slide. Now, from this diagram you need to convert to a transition table. In the transition table of Murray machine, what is being important? State associated with output. So, state and one output column will be there. Rather than that, input columns will be there as it is like in the case of DFA and NFA. So, A on sync 0, where it is going to state B, what is the output of this B? How did I get you? Again I am repeating you, again I am trying to repeat. A on sync 0, where it is entering? It is entering to state B, and what is the output of B? B, small letter b. Alright. So, how do you manage this? This B corresponds to this, A corresponds to this, it will match, definitely it will match. See, next A on sync 1, it is coming to itself A given, what is the output of A? Small letter b, B, clear. Next comes B. Now, capital state B on sync 0, where it is coming? It is entering itself B, and what is the output of B? Output of B is small letter b. Now, B on sync 1, where it is entering? It is entering state C. Now, what is the output of state C? Output of state C is A, but it is what? It is coinciding with the particular output alphabet, right. So, definitely if we have to design this kind of transition table, we have to focus that for every input we need to put a particular output line, then it will be easy for you to understand it, clear. Now, it will be easy for you that for every state on sync each input string, it is going to a particular state along with the output. So, particular state along with the output, particular state along with the output. It is not that initial state to that output, no, wherever it is entering, that particular state output should be given to you. So, this is how you can manipulate with the transition table for that guy. Okay. So, I hope this is the way you can understand this particular concept, but if you look into the transition table properly, how the transition table is designed, because I have shown you how the transition table is associated with each other, but now how to draw the transition table according to the Murray machine, I will show it to you. See, the transition table of Murray machine comprises of the state, comprises of the inputs as it was in the case of DFA and NFA, and the output. Now, my dear students, these inputs corresponds whatever states it is entering, right. See, for the state A on sync 0, it is entering B, but B is having a state output as B. This is what it is fixed. So, for B it is the output, for A it is the output, but in some scenario you will be definitely getting different outputs. So, how to write the output in the output column, that I am trying to explain to you. See, now what I will try to do is that I will try to show it to you how to write down the output part. Okay. See, for the state A, let me get back to the diagram. What is the state A output? It is B. So, it is B. Okay. What is the output of state B? B. What is the output of state C? A. So, this is how you need to write down the output. It is very simple as it is, but I am trying to explain to you that whenever A on sync 0, it is going to state B output is somewhat and state A output is somewhat, but it is not mandatorily possible that all the time these states outputs will be similar. So, that is why in the output column what you need to assemble, you need to compare the states which is present and that state output should be mentioned over here. Clear? Now, let us go into the next example, design of a Mealy machine. Okay. Now, let us check it out how to design this Mealy machine. It shows it is asking that construct a Mealy machine that takes the set of all strings over this one and produces A as output if input ends with 1 0 or produces B as output if input ends with 1 1. That means, let me take an initial state. Okay. See, produces A as output. Now, I cannot take A as the the state name. I will take suppose Q naught. I am taking one more Q 1. I am taking one more state Q 2. Now, see, construct a Mealy machine that takes a state of strings of over 0 1 and produces A as output if input ends with 1 0. If the input ends with 1 0, then the output will be produces as what? A. Clear? Now, I am not drawing a Mealy machine right now, I am drawing a Murray machine, okay? Because I will show you how to design a Mealy machine, it will be very easy for you. Next, and produces B as output if the input ends with 1 1. 1 already came, and if I draw a 1 transition to another state, say suppose Q 3, I can get the output as B. So, B is also got it, okay? And 1 0 for 1 0 I got what? A, or produces B as output if ends with 1 1. So, this is also been done. Otherwise, it produces what? C. Therefore, other states will be what? C. I hope this is the Murray machine that you have got it. Now, I will try to design the Mealy machine very simple way. See, okay. See how to do it. This one input symbol, now okay, one more thing is that before going into the Mealy machine design, we need to first check whether this is falling into the restriction part or not, DFA properties has been satisfied or not. From Q naught, there is no input alphabet for 0. So, can I take a self loop of 0? Yes, it will not hamper anything, right. So, 0, 1 0, 1 0 is ending over here only, see. And if we take 0 1 as the sequence, it is reaching C, which is not being asked in the question, see, not being asked in the question. Now, for the state Q 1, there is both the input string 0 and 1. So, does not have any problem. Now, can we take a particular self loop for Q 2 state and 0 and 1? Can we take this particular concept? We cannot take it. Why? Because if I take 0 and 1 over here, then A will produce the output 0 0 also, A will produce the output for 1 0 also, A will produce the output for any sequence. So, I cannot take this particular concept. What I can do is that I can use a particular dead state for it if you want. So, I can take a dead state for it, and for dead state what it will produce the output? Definitely C, otherwise it produces C. So, therefore, I can take 0 comma 1 for both the strings, and this one I can take 0 comma 1. This will not produce any kind of output, some or the other 0 comma 1 it will give you the output as C. So, this is mandatorily not that much of importance. So, I am not using that much of using this particular concept a lot. I am just sticking on to this particular part. Okay. Why? Now, I am trying to explain to you that how to convert this Murray to Mealy. Okay. So, how to convert this Murray to Mealy? See, in Murray output is associated with the states, in Mealy output is associated with the input transitions. So, some way or the other it should come over this particular transitions. Okay. Now, let us check it out. In the state Q naught, for the state Q naught, this input transition is entering Q naught, therefore, 0 slash capital C, and why C? Because output of this particular state is C. I am done. Next, check input transition 1 entering into state Q 1, what is the output? It should be C. Next, this one transition where it is entering Q 3, what is the output of this? B. Then 0 entering Q 2, what is the output of this? A. So, now what you will do? You will simply erase this particular thing, and now you got the Mealy machine. So, this is how you can convert a Moore to Mealy. So, the most easiest way of approaching this kind of question is that first draw the Moore machine and then draw the Mealy machine. It will be easy for you to do the approach part. And if you look into the transition table of it, now the transition table will differ what I have spoken to you in the previous time, that now the state, for every input there will be an output, for every input there will be an output. This is how you need to design the transition table. I hope this is the basic understanding question of Moore and Mealy machine. So, now let us discuss few of the questions that I have given to you. First question is that construct a finite machine with output that takes the, this is a practice question, you try to do it on your own with your either with Moore or Mealy. First question says that n strings over a b and counts the number of the number of occurrences of the substring a b b. Whenever we see a b b, we need to count the number of occurrences. How to do that? One thing we can do that whenever we reach b, suppose the output should be as x. Okay, I am just trying to say you the logic, you try to design the machine. Okay. Then if I say suppose a b b, then it should produce as x. Suppose I say a b b, it should produce as x. So, overall if you look into this string, how many times a b b has occurred? X output, how many times you got it? 3 times, therefore, a b b will be occurring as 3 times. So, this is how you need to design. I hope you have understood it. See, whenever you got a sequence of a b b, whenever b ends, wherever is whatever it will be the state, it should produce the output as x, otherwise it should produce as y. I hope it is clear. Now, how many times of x is appearing? 3 times, therefore, 3 times a b b will be occurring. So, this is how you need to design it. First try to design a Moore machine and then try to convert into Mealy machine. Okay. Next slide, next question, again the same type of question. It is asking that now this time they have defined a particular output alphabet C and prints 1 as output for every occurrence of a b. If I say a b a b b a a b, that means wherever it is terming as a b, it will produce as 1 1 b a, no a b, yes 1. So, that means how many times 1 has been appeared? 3 times. So, therefore, a b will be appearing as 3 times sorry. So, this is how you need to find out, how you need to calculate the designing process. Now, how to do this kind of designing process? As simple as that we have designed in the first example. Okay. First try to design the Moore machine as a part of a practice and then try to convert into Mealy machine. Clear? So, overall if we look into the differences between Moore and Mealy, we are come across with few points. Output depends upon the present state and present input. This is the first point which we have discussed in the first slide, and Moore machine output depends upon the present state. Okay. So, Mealy machine input transition, output machine, Moore machine states. Okay. Then it has fewer states, it has more number of states. Why? Because in Moore machine the output is associated with the states. So, definitely what it will do? It will keep on increasing the state. But if we talk about the transitions coming to the state only, present state. So, definitely the states will be reduced. Then the value of the output function is a function, the transition and the changes, okay, when the input logic on the present state is done. So, present state input logic to the present state is done, then we will be getting the exact output transitions, okay, which will be associated with the input transition, but on the contrary here it will be associated with the present state, that is it. The Mealy machine reacts faster to inputs and they generally react 1 clock cycle later. So, this is a small difference which we should understand related to the time and speed, okay, of both the machines. Now, if we look into the application part I am just trying to assemble these few points. Later on I will be discussing overall applications of all the finite machines, but right now I am just trying to give you the names of where these machines are working on or being applied, so that later on you can try to relate on that. So, you can heard about the write enable part, okay, left enable, right enable in static RAM. There it is being used, the Moore machine part. Why? Because it is associated with output is associated with the states. So, everywhere the states will be enabled, rightly enabled, then it will be then this concept of Moore machine can be utilized. Next, elevator. If you talk about an elevator, elevator is a good example, because everywhere, every position, every lift, every flat positions, you will be having one processes. So, that is why we can say elevator is a very good example for Murray machine, because Murray machine output is associated with the processes or states. Okay. Then finally, Mealy machine we can have in all the processors we are having, because everywhere input transitions and the present state. So, we can look into the processor part and explicitly use in cipher machine. So, we will try to look into few of the basic things, so that we can try to you will be able to relate with these kind of applications. Okay. So, this is all about your Murray and Mealy machines, and we have tried to analyze the designing part. Later on we will come across with one or two more examples in order to understand the conversion process of Murray to Mealy, Mealy to Murray in the next video lecture. Thank you for watching the video.